Traditional methods for creating 3D clothed avatars rely on physical simulation, are limited in realism, and require expert clothing designers. Machine learning methods promise to address these problems by learning statistical clothing models from data. In this work, we focus on learning a clothed human model from raw 3D point clouds that is detailed, copes with varied clothing topology, and can be animated by using simple body model. The key to this is a new representation of 3D shape with the following properties. First, the representation should support articulation. Like a parametric human body model such as simple, articulation allows us to easily control and generate new animations. Second, to support various clothing types in a unified framework, the representation should be flexible enough to handle different and changing clothing topologies. Third, it should support fast inference, which is required by many real-time applications. However, none of the existing 3D representations can satisfy these requirements. 3D meshes are fast in inference, but are not flexible with varying topology. Moreover, they require surface registration as a data preparation step. Implicit surfaces can represent various topologies with details. However, the inference is typically time-consuming. As a middle ground, representing shapes with deformable surface elements is promising. This approach is locally coherent and can deal with varied topology. However, the existing approaches are either limited in their expressiveness or generalization ability. In this work, we introduce scale, which meets all the requirements above. Scale represents clothed humans with hundreds of local surface elements parameterized by a neural network. Each element is articulated by the underlying body pose and is fast to evaluate. By combining a large number of elements, scale can also represent different topologies in a unified manner. Surface normals and texture can also be modeled so that meshing and rendering can be applied. In addition, scale can be learned from raw point clouds without surface correspondence. This is achieved by a carefully designed architecture that addresses limitations of existing methods that use surface elements. One of the most popular methods of this category, AtlasNet, predicts the absolute location of points in space without considering articulation. Articulation is critical for modeling clothing on humans. To address this, we predict residual clothing differences from the body in an unposed canonical space, and then apply articulations using the known body transformations. By applying this technique to AtlasNet, the result is already greatly improved, but still lacks sharp details. This problem originates from their use of a global shape code. For either modeling with a single global patch as in AtlasNet, or many local patches as done in the point compilation network, learning shapes from only global statistics is insufficient and does not generalize well. We replace the global features of these methods with much lower dimensional local features. Given an input body, we record 3D locations of the points on the body surface using 2D parameterization called UV positional map. Each valid pixel on the UV map corresponds to a point in the 3D space. This way, we can extract the local pose features for local shape regression using 2D fully convolutional networks. Additionally, we feed the decoder the UV coordinates to distinguish each element and provide the proximity information between patches. Assembling these components together, our model for clothed humans takes a posed body, encodes it into local features on articulated body locations, decodes them by deforming local elements into patches, and outputs a clothed body as a collection of such patches. We compare our method with state-of-the-art clothed human modeling methods. CAPE learns parametric mesh models from registered templates and has difficulty modeling topological change. NASA uses an implicit surface representation, supporting various topologies, but it often suffers from ghosting artifacts, requires watertight meshes for occupancy training, and takes cubical time and space to evaluate the occupancy values. Scale, on the other hand, learns a model from point clouds and supports fine-grained clothing deformations with topological changes. The dense point cloud can be directly rendered into realistic images using a state-of-the-art neural renderer called SimplePix. For more details, please refer to the supplementary text. In summary, we introduce scale, a highly flexible explicit shape representation using a large number of articulated local elements. Scale is fast, expressive, and highly generalizable to unseen poses. As a result, scale enables learning of high-quality clothed humans from point clouds without surface correspondence. The code will be released for future research of clothed human analysis and synthesis. Thank you.